So, the title of this presentation is Optimal Control of a Stochastic System with State Constraints. And I'm going to start by defining in a little more detail what I mean by that. Optimal control means that we want to minimize a cost of some sort. In this case, we want to minimize the expected cost per unit time over an infinite time horizon of this cost function. And this function is quadratic in the control action u plus some arbitrary function of the system state x. And the dynamic system that we want to control optimally is described by this differential equation, where W is a white noise disturbance. Now, in this system, the noise and the disturbance enter in the same way. And that means that it's always possible to counteract the disturbance with control action. Also, we don't impose any bounds on the control, because if we did that, then we might not be able to satisfy the state constraints. The state constraints simply say that the system must stay within certain operating parameters. For example, we might require the temperature of a reactor to stay within certain bounds, or the speed of a motor to stay within certain RPM values. Our model doesn't say what happens if we violate those bounds, but we want to control the system so that the bounds are never violated. Mathematically, we might say that there's an infinite penalty for violating the bounds. Now, to solve this optimal control problem, we use the Hamilton-Jacobi-Bellman equation. This equation was formulated by Bellman in the 1950s. That's about 100 years after Hamilton and Jacobi died, by the way. They were not active collaborators on this. So what we want to solve this equation for is the so-called cost-to-go function v, which implicitly defines the optimal control given the state of the system. What's making things a little bit complicated here is that v is infinite on the boundary, and this will cause problems when we try to solve this equation numerically. And that brings us to the most important part of this presentation, which is this variable transformation. Instead of solving for the cost-to-go function v, we will solve for a function z and a matrix function k. And we don't define v directly, but instead we define its gradient in relation to the gradient of z. And this matrix k here gives us a lot of extra degrees of freedom. So for example, if our system has two states, then k has 4 elements, and we get 4 extra degrees of freedom in each point. And that means that even though there was only one solution to the original problem formulation, we now have a whole set of different solutions to pick from, and we can pick one that is easy to solve for. Since we're dividing by z here, the gradient of v becomes infinite as z approaches 0, and that gives us a way to deal with the state constraints where we need infinite control action. Now, before we came up with this, we used another variable transformation where v was the log of z. As far as I can tell, that one was first used by Fleming in the 70s, and it works really well when the control cost is inversely proportional to the noise covariance. Then we can cancel out the nonlinear terms. But because this log transformation only gives 1 degree of freedom, we can't do that when we allow arbitrary cost and noise matrices. But it was this transformation that inspired this new one, of course, and in the case where it can be used, it actually gives the exact same function z as this new one does. Now, one problem with defining the gradient of v instead of defining v directly is this. if we were to define the gradient around the loop so that we can go up and up and up and up and get back to the point where we started, then the function v doesn't exist. So we must somehow make sure that this never happens. Luckily, there's Poincaré's lemma, which says that if the Hessian of v is symmetric on a domain that has no holes in it, then we're good. So we introduce a set of equations that ensure this. And those equations only take away slightly less than half of our new degrees of freedom. So we still have plenty of those. So let's look at what the Hamilton-Jacobi-Bellman equation has become after this transformation. The symbol rho here is short for this. Now, this might look complicated, but really it's not. If we look at this equation, we see that for a given k, this is a linear eigenvalue problem in lambda and z, except for this term, rho divided by z. The boundary conditions are homogeneous, and normally that's a very good thing, but we might be worried about, again, dividing rho by 0 here. But here's the nice thing. Since we have so many degrees of freedom, we can simply choose k in such a way that rho becomes 0 in every point, and then this term disappears. And then we're ready to solve this problem numerically. So we started with the Hamilton-Jacobi-Bellman equation, which is a partial differential equation, and we replaced it by 3 different things. An eigenvalue problem, which is also a partial differential equation, and then the condition that rho equals 0, which isn't really a differential equation because it doesn't have any derivatives in it, but it is an equation that applies in every point on our domain. And then we have the set of partial differential equations that were given by Poincaré's lemma. Then, on top of all this, we introduce an objective function. This has nothing to do with our original objective to minimize the cost. This is a new objective, which is just to say that since we have several solutions to choose from, we prefer the smoothest ones. And that way we get rid of all the leftover degrees of freedom and we get a well-defined solution. Then we use a software called ProOpt to discretize this problem so that we get a nonlinear programming. And then we can solve this using a commercial NLP solver like SNOpt. But now we're solving an eigenvalue problem with an NLP solver, and that's not really efficient. So we're working on an algorithm that would look more like this, where we have an eigenvalue solver that interacts with a nonlinear solver to get a solution much faster. This is work in progress. Finally, I thought we would show a numeric example. We take a simple two-dimensional system, which is essentially a double integrator, but with inputs on both states. The state constraints here are simply a square defined so that both states must stay between -1 and +1. And here's the solution to that problem. We see Z on the left here, which has a relatively smooth shape with nicely spaced isocurves. And given this Z, we have computed V by integrating its gradient from the definition. And that's shown here on the right. We see that the isocurves become more and more densely packed as we get close to the boundary, where the gradient is infinite. And the funny thing here, you can see here that the curves are closer to each other at the top and bottom than on the left and right sides, even though each curve has to go all the way around. And that's a variation of the famous hotel paradox. Anyways, now this solution was obtained using 6 × 6 collocation points. It's usually a good idea to try and increase the number of collocation points and see if the solution changes. Because if that happens, then we have some kind of numeric problem. Maybe we didn't use enough points. So here's the solution using 12 times 12 points instead. If you were paying really close attention, you might have seen the lines shift by a pixel or so, but I'm going to say that 6 times 6 was good enough for this particular problem. But then what would happen if we went the other way? Here's a solution using only 3 times 3 collocation points. It's not the same, of course, but in some cases maybe this would be good enough. And being able to use fewer points makes a huge difference with higher order systems. So for example, 3 times 3 times 3 times 3 is much less than 6 times 6 times 6 times 6. So this is a way to reduce what Bellman called the curse of dimensionality, or the fact that the number of points increases exponentially with the number of states. Here's a plot of the residual in the original Hamilton-Jacobi-Bellman equation. We can see that the residual becomes smaller as we increase the number of collocation points. The residual is also 0 in the actual collocation points, and that's sort of by definition how a collocation method works. But since we divide by z, the residual is actually infinite on the boundary where z is 0. Fortunately, this is not a problem, because the probability of the system being there goes to 0 faster than the residual diverges. So the expected value of the residual is still bounded. Finally, here's a plot of the 4 elements of the matrix K for the 12 by 12 solution. There are a few things that are interesting to note here. K is almost antisymmetric everywhere. So the 1, 2 entry here is almost equal to minus the 2, 1 entry here in every point. I'm not sure what the significance of this is, but it's interesting. Even more interesting is that each of these 4 functions is relatively constant. The variation within each element as function of the states is much smaller than the difference between the different elements of the matrix. And also we see that these functions are relatively nice and smooth. So this means that they can be well approximated by low-order polynomials. And again, that is why we think that this method is so promising. We get good results using few collocation points, and we can mitigate Bellman's curse of dimensionality. And that concludes my presentation. Thank you for listening. Thanks also to my co-authors, Torsten Wieck and Klaus Breitholtz. The report that this presentation is based on can be downloaded from the Chalmers Library webpage on any of the links shown here. My name is Per Rudqvist. If you have any questions, you're welcome to email me. I've also submitted this paper to CDC 2014 in Los Angeles in December. So if it gets accepted, then you can come there and see me in person. Thank you.